I thought I'd do a quick blurb on the technical aspect of this Volvo tach thing I did. There's the guy from the video. As I mentioned in the video, I wanted to make a 6-cylinder tach work on a 4-cylinder engine, which means I'm going to have to change the sensitivity of the tachometer and keep it linear, make sure that the proportions still work out the same way. So I reverse engineered this unit. It's a VDO. They're pretty common instruments manufacturer. The others you might see would be Smith's, Veglia, I don't know who else. But anyway, I immediately noticed that this looks a lot like a 555 with a one-shot configuration. It's got a resistor, capacitor, time constant as expected. Every time an ignition pulse comes in, it triggers the one-shot. This would be pin 1, the input, pin 2, the input to the chip after some filtering. And then X was my theoretical idea of the output inside this chip of the one-shot circuit based on this RC. The idea being that X drives a current source who is making a constant current into the meter every time X is on and no current when X is off. And you go and you think about this in proportions, it's a pulse density modulator. So as the frequency of the input pulses increases, the frequency of the output pulses increases at the same time, but the pulses remain of the same height and length, height and duration. So it's the density of the pulses that changes the average current into the little electromagnetic movement in there. It's a fairly linear relationship between current and meter deflection. So yeah, instead of varying the current, they just vary the average current via a pulse density modulation. And I drew this little bit here just as an example of what's probably going on inside. Based on my scope measurements, I'm assuming there's a current source whose emitter has a 131 ohm calibration resistor on it. That sets up the magnitude of the current of the output pulses into the meter movement. So I wanted to make this more sensitive by a precise proportion, so respond to a 4-cylinder engine correctly. So I had to decrease this resistance, this one here, to increase the current at the output. This affects the upper range, in the 5,000 to 7,000 RPM range of the meter most prominently. And then adjust afterwards the time constant of the one-shot generator, and that sets up the bottom of the meter movement's range. I won't get into an explanation of why it's done that way. One might assume that the whole thing is done on this end, just on the pulse width, but you have no way to, calibrate the top end of the meter's range just on one adjustment. So you do the bottom and the top. They obviously designed these so that the top of the range is done in a fixed manner, and once it's done, it's done. I'm assuming they didn't feel that there was a need for quite so much precision up there. I mean, you're not caring whether you're at 7,200 RPM or 7,000 RPM. You shouldn't be there anyway. But certainly below about, kind of as you're out of the red line, actually, I noticed. Yeah, right as you're getting about 5,500 RPM, this circuit, the one-shot circuit in here, sort of takes over and defines the rate of change of the meter for input frequency. So anyway, yeah, I modified it. I reduced this resistance to increase the current, and I dialed it in to get the top of the range calibrated so that it's correct. And then I found that the adjustment range of the one-shot circuit was large enough to bring it in the bottom end, at 1,000 RPM or whatever, and the whole thing is pretty much linear. I'm going to finish linearizing it with these. That's what these tabs are for. All they do is change the amount of reluctance in the magnetic circuit around the coil, just to change the current to force relationship of that mechanism, which of course is working against a pair of counteracting clock springs. This is very nice, mind you, I must say. This whole thing is very carefully designed to be totally dynamically balanced. It doesn't care whether it's upright or pointing down like this or up like this. It will always indicate the same speed all of these little brass weights, and you might see there's actually threading in here. They turn and then they glue them down. They've adjusted all of these very carefully so that this whole thing is balanced, irrespective of its orientation relative to gravity and to the acceleration of the car body. Just a little bit of a side note. Quite a nice bit of engineering, just to show you engine speed. So for anybody who's curious and wants to mess with one of these are in BMW, Mercedes, Jaguar, Volvo, Ferrari, whatever. They're in all sorts of European cars, and they mostly seem to follow this same circuit. And you're going to see variations in this resistor, and I think I've seen in a few others different resistances elsewhere in the circuit, but the critical aspect is going to be this resistor here, and then adjusting that trimmer and potentially changing the timing capacitor in order to bring it into range. So ask me questions if you want. I didn't fully analyze everything. I didn't really look too heavily into what pin 8 does. My own question to viewers, if anybody watches this, is what is your 131 ohm resistor in your tachometer? I would assume if you're in a Volvo and you've got a 4-cylinder engine, and you look down here, if the board layout's the same, I'm not sure. But if you look at that resistor right there, the blue one with the brown, orange, brown, red, or sorry, yeah, brown, orange, brown, red, 131 ohm, 2%. I'd assume that resistor is going to be a different value, somewhat closer to 100 ohms or something. Or maybe they changed something else about it, I don't know. They could have, there's a few things they could have done. But that's kind of a little look in the VDO tachometer from the 70s, which I'm guessing they've used probably over a 20 or 30 year period leading into the 90s, maybe even later. All right, have fun.